My name is Stephen Payne. I'm a senior here at Carolina, and I am a neuroscience major who's interested in going into pharmacy. I've loved organic because of how it relates to drug design and synthesis, and I'm extremely excited to apply that to my future career. But currently, I would love to transfer the passion that I've had for this class to students next semester in organic as well. I've been able to be a peer mentor this semester for 102, and I have really enjoyed getting to know the people around me and getting to help people who have had questions. I've grown relationships with these students. I would love to transfer those skills that I've made, those people skills that I've made in 102, and how I've learned how to best help people with empathy, with compassion, and use that in organic where I know people can get frustrated quickly. I would love to have that empathy to, I've been where they are, and I know how I can help them best. I would suggest to them, principally, to always use the workbook. I know it's easy to ignore sometimes, but when you use the workbook, you are consciously growing your skills. And then when you take it to review sessions, that's the other important part, you're able to see what you got wrong and to learn more about the material. And it's important to go to those sessions with a growth mindset because sometimes you can get really frustrated when you get things wrong. But I know that when you go with an open mind and you do what you can to strive with the material, you'll be able to be really good at organic chemistry. So the problem that we want to solve here today, we have a cyclobutane with an ethyl substituent, and we have an alcohol functional group. We're going to react this with hydrogen bromide. So this will go about in an SN1-like fashion. We're going to have the hydroxide pop off here, and we'll make a carbocation. Now normally, hydroxides are really bad leaving groups, but when we react them in the presence of a strong acid, like hydrogen bromide, that hydrogen will protonate the most basic atom, this oxygen, and we will activate to make a much better leaving group than the hydroxide. This is now water. So this water will pop off here and will form a carbocation like this. Now, let's look at the carbon structure to figure out what we should do next. We see we've got a cyclobutane, and we have a positive charge here, a carbocation at position 1. Now we know that cyclobutane, the bond angles are at 90 degrees, that's not particularly stable. And carbon rings really want to be in 5 to 6 members. So when they can make a ring expansion, they will. So what happens is this carbon here at 5, this bond with 2 breaks, and it attacks this carbon at the 1 position. So down here, we see we've got carbon 1, carbon 2, 3, 4, and 5. Carbon 1 filled its octet, and carbon 2 lost its octet, so the positive charge moved there. Now, we've got a trigonal planar structure here, so these electrons can attack above or below the p orbital. So we could end up with an asymmetric center here, above or below. After, the bromide from earlier will attack this carbocation, and it's a similar thing. It's attacking a p orbital, an empty p orbital, so it can attack from above or below this trigonal planar section of the molecule. So if it attacks from above, and we have this constant or stereoisomer, we get above or below, and then with this stereoisomer but below, it can again attack from above, or it can attack from below. So what we end up with as a product is a diastereomeric mixture.